Section 15.3 is kind of short, and it's basically a direct result of what's in section 15.2. So it's supposed to be mostly about how you would get the area of a region in the plane by double integration. Presumably not a rectangle, since those are pretty simple, but if you have some weird shape, right, like where you've got a shape that's bounded by a couple of functions, where then getting the area by other methods would be kind of hard, then this would be a way that you could do it. And this is the formula where if you look at it, it's like, oh, this looks weird. It looks like something's missing. Between the double integral sign and the dA, it looks like something should go there. Really, there is a thing there, which is just 1. And the way that I think about where this formula comes from is this down here, where I think of it as basically just a special case of the way that you would get volume under the curve. So if you think that's what a double integral is, where at least that's an application of it, that you can get the volume under a curve and above the xy plane, then what if the curve is z equals 1? Then that shape that you're getting the volume of, that's solid, it's always going to have height 1, so therefore its volume would have to be equal to the area of the region in the xy plane that you're integrating over. So that's how I always thought of where this area formula up here comes from, that it's just sort of a special case of sort of the general way of getting volume under a curve that you see earlier in this chapter. And for the first example of this working, I picked one where you obviously don't need to do double integration because it's a triangle, right? So you could just do this. And that's sort of the point. I wanted one where we could say like, okay, look, clearly this works. So you get the thing that you're supposed to get. So we want the region bounded by y equals 3, x equals 4, and 3x plus 4y equals 12. So y equals 3, that's up here. That's the top of that triangle. X equals 4 is the right side. And then with the 3x plus 4y equals 12, I just got the two intercepts. And I said for this to work out, the x-intercept's got to be 4, y-intercept's got to be 3. So you get that diagonal right there. And sure, if you want to do the area the conventional way, right, it's a triangle, so 1/2 base times height. And I guess I was thinking of the base as being that, but I suppose it doesn't make too much of a difference. 1/2 times 4 times 3, yeah, you get 6, right? Okay, sure. So just to go through one where we can see like, okay, this does actually work, I have this one set up to go dy dx. You could do dx dy, it's about the same level of difficulty. But I said, all right, if we're going to go dy dx, then when we're going to have the limits of integration for y, they've got to be, well, it's going to be this line down bottom, right, the diagonal line, and then y equals 3 is on top. So then we've just got to solve this one down here for y, right? And that's what this is right here. So eventually you do that, you get that y is equal to 3 minus 3/4 x. So that's the thing on the bottom. So that's the lower limit. Upper limit's 3. And then the x values are going from 0 to 4. So 0 to 4 right there. I always write in the 1. You don't have to if you just have the double integral sign and then a dy dx. That's totally fine. But it feels weird to me not to have it there, so I always write it there. And then integrating 1, you would just get y, double evaluate that. Eventually what you end up with is 3/4 x. And we've got to integrate that with respect to x. So 3/8 x squared, then evaluate that from 0 to 4. So that really just ends up being 3/8 times 4 squared, right? Because then the other part, when you sub in the 0, you're going to get 0. So you do just end up with 6. Okay, so you get the thing that you're supposed to get. All right, good. So it looks like this works. And then I did put the other order on here as well. If you want to go dx dy, then if I scroll up just for a second, then this diagonal is always on the left. X equals 4 is always on the right. So then you just have to solve this right here for x. And that should be what goes on the bottom, right? On the bottom, that's the lower limit of integration. So yeah, 4 minus 4/3 y. 4 is always on the right, and the y values are going from 0 to 3. So that would also work. Example 2, now for one where if you tried to get the area by conventional methods, it would be a lot harder. And this would be one where being able to get the area by double integration is actually helpful, in the sense that it would probably be faster. In example 1, certainly not, right? 1/2 BH is faster than the double integral. But here I think the double integral is going to be a little bit faster. So I just graphed all three of these and I said, all right, well, x equals 4. I think I actually stuck that in last. I got the other two things in first, but it's this, right? It's this vertical line right here. I think what I did is I probably graphed the square root first, then graphed y equals 2 minus x. But the square root, all right, that's going through the origin, going through 1, 1, going through 4, 2. I guess next going through 9, 3 if you want to have points where both coordinates are integers, but that would be way, way, way out there. Then 2 minus x. So there I just said, all right, well, there the y-intercept is 2. The x-intercept is also going to be 2. And then, I just plotted a few extra points just to get that to look relatively decent. And also to get the points of intersection, because those are the key things, right? When you draw out this shape, it's like you want that point, like you need to know what it is, right? Where the square root of x and 2 minus x are going to intersect. And you need to know what that point is, and you need to know what that point is. Otherwise, it's kind of hard to get the limits of integration right. But the shape that we end up with is sort of an imperfectly cut piece of pizza type shape. And yeah, that would be a little tough if you didn't do it this way with the double integral. So, all right, we go down here. So I did it as dy dx because in this case, dx dy is harder. It shows up at the very end, but basically if you're doing, what's on the left, what's on the right is always going to be x equals 4, but what's on the left, sometimes it's this, and then sometimes it's this. So dx dy is going to be tougher. Dy dx, it's like the square root of x is always on top, 2 minus x is always on the bottom. So that's just one double integral. That's going to be the better way to go, I think. So, all right, well then the limits of integration for y, thing on the bottom is 2 minus x, thing on top is the square root of x, and then for the shaded in part, the x values are going from 1 up to 4. So there are those limits of integration. And then, again, the integration itself is pretty simple, right? You integrate 1, you get y. Double evaluate that, you end up with the square root of x minus 2 plus x. Integrate that with respect to x, and then double evaluate that at 4 and 1. So there's what you get when you sub in 4. Then there's what you get when you sub in 1. And eventually you need to get a common denominator to simplify this thing. But it's just a bunch of algebra, right? And that's sometimes the thing you got to do. But you end up eventually getting 37 over 6 as the area. All right, well, that way, like for this particular shape, I think is faster with the double integral. So that's one where I think it's necessary. With example 1, it's not, right? But then I also wanted to kind of point this out, so I just kind of wrote it at the bottom. If you go the other way, you can do it if you want to go dx dy, but it's tougher because what's on the bound on the left side of that shape changes. So, look at the lower limits of integration when you integrate with respect to x. They're different there. So you would have to do something like that. It's doable, but it's longer. I guess if you really wanted to do it that way, though, you could. Getting the area of a region in the xy plane by double integration is the biggest point in this section. But this is sort of a cool little thing that's also in here. There's only one problem on the homework list that relates to this, but I like this thing, and it was on the template that I got for covering the course material. So this is fun, where the average value of a function over some region you can get. Even when it's some weird shape where trying to get the average value seems like it'd be really hard. And it involves a double integral, and you just have to divide that by the area of R. So, like if you wanted to get the average height of this paraboloid, right? Because that's clearly what this is, right? Over this rectangle here. If we're doing it over a rectangle, getting the area of a rectangle is easy, right? Length times width. So you go 3 times 5. Area is going to be 15, right? So then the average height, 1/15. And then I did it as dy dx, although certainly you could go in the opposite order if you wanted to. I did it with dy dx because I wanted to do the integral where one of the limits of integration was going to be 0 first. Just because I thought, well, if I do that one first, then when I integrate the second time, maybe I'll end up with something a little less complicated because it won't have as many terms. So that's all I was thinking about there as far as picking the order, because it looks like it's the same degree of difficulty either way. But I mean, it's over a rectangle, so the limits of integration are simple, right? You wouldn't have the limits of integration for y in terms of x or anything. It's just 0 to 5. And then for x, it's going to be negative 1 to 2. So you integrate with respect to y, you get x squared y plus 2/3 y cubed. Going to evaluate that, 0 and 5. All right, well, when you sub in 0, you don't get anything. When you sub in 5, you're going to get 5x squared plus 2/3 times 125, which would be the 250 over 3. And then we integrate that with respect to x. We end up here, and then we're going to double evaluate that. So then that's what you get when you sub in 2. That's what you get when you sub in negative 1. So, all right, we end up with all this in here. And 40 plus 5 is 15, it's 45. When you divide by 3, you get 15. I'm getting ahead of myself here. So that's 15. That's 250. So then that's 265. So it's 265 over 15, which would reduce to 53 over 3. So that's another thing that you can do with double integrals that clearly ties into this stuff, right? Since this section's all about area. It's like, well, if you can get the area relatively simply, then you could also get the average value of the function without too much trouble. I mean, I guess even if you had a weird R, like a weird region that you were integrating over, you could still do this. It would just be about twice as long as this one, I suppose. But you could do it.